Okay, let's go to the third talk of today. Is my friend Farid Medjdoub from CNRS, Lille in France. Farid now will speak about the fabrication of high-power gallium nitride transistor. Farid, the podium is yours.
Thank you, Gaudenzio, for this introduction. So I hope you still have some energy to listen to the last talks, about 1 hour. My name is Farid Medjdoub. So I'm from IMN in France, which is driven by CNRS, which is the national center. These are people from my group, and we don't do growth. So we work closely with growers with several sources, and we do device processing, integration, also, of course, lots of characterization, high voltage and RF. So that's basically what we do. So just for people who do not know Lille, so this is a pretty nice city. You can see the city center here. So we are located in north of France. It's actually the Belgium border, and I'm actually living in Belgium, so you can cross the border every day. And and it's quite convenient because you can go have 1 hour from London, Paris, Brussels. So it's quite well located. Okay, so we are part of a national network of large technological facilities for basic technological research. So we are not producing any devices. We are not a company, so it's still a public research, or let's say government-driven. So you have 5 or 6 big clean rooms in France, so 2 in Paris. And then in Besançon, Grenoble, Toulouse, and we are here. And each clean room has its own specificity. So in our case, I don't go through the others, but in our case, we do high-speed devices, so RF and also high voltage, but there are also some opto and microsystems, so it's pretty large. So here's the lab from outside IMN, and this is a top view of the lab. You can see it looks like 2 clean rooms, but actually they are connected here, so you don't have to go in and out. So they are really well connected in the clean room environment. It's about 1,600 square meters, so it's pretty large. So one of the largest in France. And that's where we work. So today I will start with a short introduction. I will show you some device design for high power, at least what we use for high power devices. So I'll focus on a couple of features. I'll describe the device design. So for people who knows processing, this may be a little bit boring. This will be very basic. But I will go through, I've been asked to go through also this, let's say the processing techniques, so photolithography, etc., and also the main technological bricks. So after doing that, I will show you what we specifically do. One of our tasks within the European project InRel, where we try to push the breakdown voltage limit of these GaN on silicon devices based on the local substrate removal. So I will describe that later on. Okay, so as mentioned by the other speakers, I think you're all convinced that gallium nitride is probably one of the most important, if not the most important, new semiconductor since silicon. And there are lots of promise, saving energy, carbon emission, enable totally secure communication at very high frequency. So you can have, today you already have blue, green, yellow, all kind of colors by adding more and more indium. So this is things that you obviously see. That's a chart, a graph that I like here is for people who are in the field also for a while. Like Gaudenzo, I think you started end of 90s, if I'm not wrong. We started early 2000, 15 years ago, early 2000, gallium nitride. So we were here. And this is the number of, let's say, patents or main patents versus time. And it's amazing to see, especially for early players or actors, it's amazing to see that very big companies like onsemi, Infineon are making products, and also in RF side, and of course the number of publications just drastically increased. So gallium nitride is really a success story, and I think it will last for the next 30 years from now. So it's definitely has superior, let's say, properties as compared to the other semiconductor, especially for power and RF application. So I just put some example here. So for, let's say, high voltage devices, what we think, we'll see in the near future, but what we think is gallium nitride will find space in the power arena, especially at medium power but high frequency, what they call high frequency, let's say 1 megahertz or so, around 1 megahertz. So there are opportunities here for this material. And at very high frequency, let's say microwave and millimeter wave, this is very clear. There is no question about it. It's definitely gallium nitride from L band to all the way to W band. It's obviously a matter of reliability, but it's definitely ongoing. From industrial point of view, we are at K band right now. So industry are qualifying, like Corvo, UMS, qualifying devices around 30 to 40 gigs, and that will increase over time. So that's the situation here. And gallium nitride has too many advantages in this frame. Okay, so quickly, I think it has been described already, so I don't spend time on that. So this clearly a breakthrough in terms of power performances. So of course, power is current and voltage. So if you use gallium nitride, this is a comparison of, let's say, a single device with the same design. What you can get if you compare to gallium arsenide or silicon, obviously using the same size and everything, you have much more voltage and much more current. And this is obviously due to its very wide bandgap as compared to the others. So the intrinsic properties of this material and also the thermal management that can be intrinsically done if you compare to gallium arsenide, for instance. So that's the practical advantage of this material. I think Geoff also very well described one of the issues we have with gallium nitride is the surface states. So you get, let's say, the 2-deck for free, but you get also surface states here. And there's no way to make devices without taking care of that. So there's inherent surface changes causing 2-deck depletion. So you have the so-called virtual gate. So the negatively charged surface state compensate donors. So you deplete basically the channel between the gate and drain region. So that's a really important issue that has been more or less solved. And one of the solutions to solve this problem is to use this thick, I like to use this word thick because it has to be, I will show you in the next slide, but at least to use an in-situ grown silicon nitride. So this has been developed at Ohmic, and more or less the same people are commercializing that for a couple of years now, which is the company Ebeam. Also here, of course, the buffer, I don't come into it, but you need high electron confinement, a low trap in the buffer and the high electric field. So this is, of course, part of the IPs from company producing these types of, let's say, growth layers. But again, the silicon nitride is used to improve the device robustness to prevent, to avoid. Also, I would show you how you have to be careful the gate leakage you have to be careful the design after full passivation. So I'll come back to this point. But definitely you have to control the surface charge from the surface charges from the growth point of view. So we've been doing some experiments for a while, about 10 years ago. So this has been done also with it was at Ohmic time here. So to show the benefit of this in-situ nitride, so these are quite old slides. So we compared cap-less AlGaN GaN heterostructure with a GaN cap, which is widely used by many companies or academics, and this silicon nitride. So here you can see, so we just ramped up the temperature up to very high temperature, 900 degrees C, and at each temperature you leave the sample or the wafer for 30 minutes. So it's quite a harsh stress, and what we monitor is just the 2-deg, so the carrier concentration. And here you can see the surface, AFM surface, before and after the full cycle of stress here. And clearly, there's no difference in terms of, let's say, structural properties here in this case. You have degradation in the other cases, and especially the carrier concentration just dropped. Of course, it's very high temperature. This is not something you use in reality, but it shows the advantage, shows the limit, or at least the benefit of this cap layer in this case. So no change in the case of silicon nitride. Also in another project, it's an old one, which was funded by the European Commission. Also, it was called GREAT. We did at that time 0.5 micron technology, GaN on silicon. And again, I don't have time to explain the pulse measurement. Some people knows here, but basically, you use question bias point where you get the ideal IDVD characteristics. Here is the blue one. And then you use over question bias points to stress either the gate or the drain or to, let's say, to highlight traps in different locations. And here you can see that it matched perfectly. So this was a good result here, showing that, at least at the gate vicinity, there was no problem of dispersion. And also the thermal stability was very nice. So we monitored 10th of devices, probably 50 or 100 here in this case. The threshold voltage and the transconductance after 1,000 hours above 300 degrees C, which is quite harsh for this is not reachable, for example, with gallium arsenide devices. So this is a high temperature. And we attributed these nice results definitely to the in-situ silicon nitride. So other partner using GaN cap in this project couldn't reach such high temperatures. So it was a way to really reflect the advantage of silicon nitride here. So another point about this very important feature, so this cap layer, is the thickness of this film. So if you can, of course, as also Geoff mentioned, you can use even lower than 2 nanometer. You can use monolayers. It's enough to, let's say, properly cover and protect the surface. But from leakage point of view and after full passivation, there are some issues. That's what at least we saw. So here you can see some very basic device, so circular diodes, 60 micron, and you can see the reverse leakage current here, which is pretty decent in both cases. So you have a device, a structure with very thin versus much thicker, almost 10 times thicker. So before passivation, you get basically the similar leakage current. If you passivate this device with very standard PECVD that we use in a routine, after second passivation, you get a very strong and systematic degradation. We've seen that on 10th of wafers of the gate leakage, early breakdown. This is this one here. So you really have a parasitic conduction injecting. I will explain this point in the next slide when using this thin and a cap layer. So we did exactly the same process on the right one. And the fact that you are much thicker here, we observed that almost no degradation of gate leakage occurs. So again, the thickness is an important parameter for this. And we tried at that time to explain the leakage mechanism. So basically, you inject from the, let's say, the gate towards the drain, and the high electric field, you activate or you have an injection, creating a conductive path at this location. We have evidence that there is nothing flowing inside the PECVD nitride, so it could only be at this interface. So again, the message here is to say that the thickness of this cap layer has to be carefully designed to benefit from it, but also preventing electron injection and the high electric field. Okay, I move to some basics, which would probably be more of interest for people who has never seen any clean room or who are not used to it. So I try to explain you how to fabricate a device here. So this is a general view of how it goes. So you start here with the specification. And according to the specification, you try to design some devices. And that allows you to produce a mask layout, which is still in software. Then in case of Optical Ito that I will explain later on, you can produce the mask set for fabrication here. And then, of course, you have to fabricate the device in the clean room. And after that, you get some chips that needs to be packaged, tested, and then this gives rise to integrated circuits. And then eventually, if you have to adjust, if you don't reach the specification, you reverse engineer and start all over again until you get the expected devices. So you can see some, let's say, pictures of the clean room. I have a video actually which show you better how it is inside for people who has never come in the clean room. So it's a fully controlled environment. That's summarized in a second what is a clean room. So controlled environment means contamination, humidity, temperature, pressure, chemicals, everything is monitored, everything is controlled, everything is measured. To give you an idea, it's 100,000 to 1 million times less particles than outside. So this is a very, very specific and expensive environment. So that's why you have very few clean rooms, even in big countries. And also the personnel working in clean rooms, some people here knows, they undergo extensive training in contamination. This is a very dangerous environment for manual operator, I will explain the difference. So they enter and exit in the clean room through airlocks and air shower, for instance. And they must wear specific, as you can see here, they must wear specific special clothing, like to design to trap contaminant. And this is like something. I mean, everything should be covered: boots, shoes, coveralls, face masks, etc., etc. So here, yeah, I just choose the two partners that we have in the project. So clean room, you don't have. I mean, all the clean room are not the same; they are classified. And the parameter is how clean the clean room is. So you have different classes. So I don't go through all the classes here, but to give you an idea, the class 1 is a foundry, such as on semi, for example, or some others, where you have no human presence. So there's no operators or whatever. So everything is through automation, and all the technological steps are done with automation. So you probably see in the video this type of clean room. In our case, we are, of course, academics, so this is way too expensive. This is for production, actually. So in our case, we have manual operators, so students, postdocs, they have to suffer to doing hardware, so real work, but it's better to learn, you know, how to do it yourself. And this still allows, of course, not with the same yield that you can have in class 1, but you still allows very nice demonstrators, prototypes in small quantity. Yeah, that's the video. I hope it works. Try with the audio. Let me check. It's about 5 minutes. Should be fine. No? Not working?
Maybe you have to go to the desktop.
Okay. Okay, I'll try here.
Welcome to TriQuint Semiconductor. Before entering the fab, there are several things that you must know in order to protect yourself, the wafers, and the cleanroom environment. The TriQuint fab is a Class 100 cleanroom. This means there are only 100 particles per cubic foot of air. In comparison, the air inside a typical office building contains up to 1 million particles per cubic foot of air. The wafers and processes in the fab are highly sensitive to particle contamination. A particle 200 times smaller than a human hair is large enough to cause contamination issues and electrical failures on our wafers. Keeping particles at bay is an essential component of cleanroom protocol. Many common items are not allowed in the fab. For example, pencils, office and copier paper, food, drinks, cosmetics including chapstick, gum or candy, and much more. Always ask your supervisor or trainer before bringing items into the fab. If you need a notebook, there are cleanroom notebooks and other cleanroom supplies such as pens and safety glasses located in the stockroom. Everything brought into the fab needs to be wiped down with DI water or isopropyl alcohol. Dust and dirt clinging to items can damage wafers and contaminate the cleanroom. We must also protect the fab and wafers from another contaminant.
Okay, I hope we give you an idea of how it is. You know, it's more like to have a very general view. So this was continued. I didn't mention this. This is the cleanroom from a manufacturer, TriQuint, which is now Qorvo, so in the US, and they are doing some gallium nitride RF devices. Okay, sorry about the poor video and the audio, but whatever. So coming back to the different techniques here. So today, GaN on silicon power devices are fabricated up to 8-inch in several companies now, or at least ongoing. And that allows you to generate hundreds of devices, even if not even more, simultaneously. So here's the basic processing steps. I just go through quickly. So like wet cleaning, photolithography, metal deposition, thermal treatment, PVD, wet and dry etching, ion implantation, wafer thinning, planarization, electroplating, etc. So you have many, many steps. I won't go through all the steps, otherwise we just stay here till tomorrow, but I will just focus on a couple of those just to give you a, let's say, flavor and idea of how complex the processing is and how many steps you need to perform to get your device done. So yeah, one of the basic steps is photolithography. So this can be done in several ways, some industrial ways, but also some academic ways. So that's optical is obviously used by universities, for example. So you use hard mask. This enables to pattern parts of thin films or substrates. So what you do is first you start with a dehydration bake to remove humidity. Then you eventually use an adhesion promoter. Then you apply your resist here, and you soft bake, and then you use your hard mask here to so we use the light to transfer the geometric pattern from this hard mask to the photoresist, and the resolution is about, let's say, 0.5 micron to 1 micron here. And then you use chemical treatments to reveal the patterns, and the resist here can be negative or positive, which means that you can get the reverse patterns from your hard mask, or the same pattern if in case of positive resist. So that's how it looks like. Maybe you didn't see in the video, which was not that good, but here is the litho room where, of course, the light is very specific not to degrade the sensitivity of the resist. So that's why it's kind of yellow. So you can see different view of the rooms here. Here and here you can see the equipment to manually align wafers. That's an example of a hard mask, and that's that's a wafer that is under exposure. And this is just an example of the patterns you can get. So it's about 2 micron separated by 1 to 2 micron here. So this is the thing you can get from Optical Ito. And this is widely used in, for example, in our case, for making some demonstrators. Of course, for production, this is not something you can use. So there are some other technique, like a stepper. It's obviously more expensive, but this is the way to make millions of devices. So it's the step and repeat camera. This is how the tool looks like. And again, this is used to manufacture integrated circuit. It uses some alignment mark to align each reticles with a very good resolution down to hundreds of nanometer, for instance. And here is the description of the equipment. So you have a laser source, computer console to control the equipment, the exposure column here, which is pretty large, the wafer to be exposed with the reticle here to be to pattern the wafer. And the last litho technique is the Ebeam, which is also not for production. So this consists in scanning a focused beam of electron to draw custom shapes on the surface covered with an electron-sensitive film. So you don't need any hard mask for that. So it's really direct, what we call writing with electrons. So of course, the advantage is definitely the resolution. So you can go sub 10 nanometer resolution with this tool, with the direct writing. And yeah, one point I mentioned is, of course, you have high resolution, but low throughput, limiting the usage to basically you can write the mask, produce the mask, but for low volume production. So basically for research and development. So at IMN, we are lucky, we are well equipped. So we have 2 E-beam, as we do lots of high frequency devices. So you can see the 2 E-beam here. Here you can't see anything, actually. It's just the description of the tool. I, of course, won't go through, but it's just to show you how complex an E-beam is. And this is about more than $1 million. It's not just the cost of the equipment, 1 million here and there. It's the maintenance that costs. It's about 100 to 200K per year maintenance. So that's why very few labs has this kind of tool. And here's an example. That's a very nice pattern here. You can see the scale. It's about 100 nanometers square space with a spacing of sub 10 nanometer. So this is very challenging patterns. And here's some lines of way below 50 nanometers. So that's the thing you can do only with Ebeam. Okay, I move to etching now. So I go through again, as I mentioned, through the different or the main techniques. So I try to go fast. So etching, basically after your litho here that you define, whatever the type of litho you use, you can do dry etching by plasma or wet etching with chemicals. So the important factors are uniformity, etch rate, and control, and etch selectivity. So of course, there are some advantages and drawbacks in both cases. So the wet etching provides low damage. This is key. High selectivity. The equipment is pretty simple. It's basically based on chemical. But of course, it's isotropic. As you can see here, you etch in any direction. It's needed sometimes, but not always. So if you want to etch, let's say, isotropic, that's not the good solution. And one important point is there is no real efficient solution of wet etching for gallium nitride. So it's not a real option to make deep etching or whatever. So for GaN, we generally use dry etching. It's quite lower cost, at least as compared to wet etching. It's anisotropic, so it's you etch almost in one direction, more or less. However, when you reach the semiconductor, for example, you have plasma damage. You have to be careful with that. So you have to play with the power, not to, let's say, damage the material. And also an important point is when you do dry etchings to avoid redeposition on no volatile compounds and contaminate your active parts, for instance. So this is also something to take care. Here is just to show you, it's again our equipment here, so you can see a bunch of equipment. So it's different tools for dry etching, RIE, ICP. So I cannot describe each, but they have different properties to do different types of etching, I would say, with different gases. And here is the places to do all kinds of wet etching or wet cleaning. So it is an example of silicon isotropic wet etching. So they play with the undercut to get some very nice shapes. To be honest, I don't know the application here, but I found it beautiful in this case. And here is a dry etching where you want, like, for example, almost 90-degree etching here. It's done dry, so that's only plasma can give you this kind of, so it's pretty deep. You see the scale is 1 micron, so it's really several micron straight. So this was used in the past, for example, for isolation devices. I will have a word on that. Yeah, metal deposition. You have also 2 techniques, let's say, to get your patterns metallized. So this is also a key technique in the device fabrication. So you can etch your metal, which is more used in industry, and in our case, we use lift-off. We can do both, actually. So the process is simple. So in the case of etching, you metallize the substrate here. Do your photolithography that I showed you with any technique, optical or Ebeam, whatever. Then you etch the metal here and remove the resist on top to get your, with solvent, to get your metallized pattern. And in this case, you use a bilayer resist. You use 1 or 2 litho, depends. This can be done in 1 or 2 steps, depends on the processing. But basically, you define, again, your patterns. And then you have also to define, by exposure, you have to define the undercut here, which is very important to lift off. And of course, these 2 resist has difference in resist sensitivity. So that's why you can get this undercut here. And then, of course, you evaporate, for instance. That's what we use for lift off. And then you will use solvent again and you will lift off these parts on top of the resist, and the other part will remain and create your metallized patterns. So there are both ways to do that. And you have different kind of metallization. Again, each one has its own, let's say, applications. So evaporation, where the metal is melted in vacuum and evaporated through vacuum. This is really widely used in 3.5 with 3.5 semiconductor, and it's ideal for lift-off. I'll show you a picture in the next slide. And you can sputter deposit also using PECVD, which consists in ejecting material from a target onto the substrate, and you use often like something like argon as a sputtering gas, and in this case you can really cover also the sidewalls and everything. So the coverage is much better than evaporation. Yeah, that's an example of tool also that in-house that we have. So an evaporation tool, actually we have several of those, different kind, and a sputtering tool. And these are some just example. This is a very short gate, mushroom gate, needed for RF. This is obviously not for power. This is very, very short, it's sub 100 nanometer gate length. This is a multi-finger, most probably for RF also, not a power bar here. And depending on which metallization, for example, the metallization of air bridges is done by electroplating, so I will show you also that. And that's the difference here between evaporation and sputtering. So it's not the same. If you look at carefully, you feel like you have the same metallization, but if you look at the sidewalls for evaporation, there's no way to metallize the sidewalls here, which is the case for sputtering. And sometimes you need this, sometimes you need that, so both are useful. And the last metal deposition technique is electroplating, because for backend, for example, you need thick metal deposition, starting from a couple of micron up to several tenths of micron. And there you cannot use evaporation or sputtering, which are limited to about 1 micron and something, 1 to 2 micron. So engineers are very unhappy if you want to use thicker, so that's not allowed. So it's too expensive actually. So you have to use electroplating, which is based on electric current to reduce dissolved metal cation so that they form a thin current metal coating. And you need a seed layer for that. So you start usually with sputtering and you grow through electroplating on that. And this is the type of let's say patterns or that you can get. So these are deep via, so there's several tenths of micron, and you need to fill in. So you start with metal here, and with a careful process you can fill in and deposit very thick copper in this case. And this is a top view of thick electroplated metal deposited. Ion implantation also is a very important one for device isolation. I will come back also to this point. So again, this is ions of a material accelerated in an electric field and impact into a solid. This is really for implanting ions. And the process is used to change, of course, the physical, chemical, and electrical properties. So the energy of the ions can be very high, so several hundreds of kilo electron volt. And this, of course, depends on the nature of the spaces that you implant. And so the depth is modulated by a number of parameters. And this is used to prepare, for example, SOI substrate, by high-dose oxygen implant, doping a semiconductor, or device isolation in the case of gallium nitride. I have two last things to show you. So the rapid thermal annealing, I just go fast here. So this is a process that heats wafer up to very high temperature, but in a few seconds. So that is needed for formation of ohmic contacts. I'll also come back to this point here. This is our tool that can go up to 1200 degrees C, and again with very high ramp here. In this case, it was a low temperature, but you can do that at 900 degrees C. So going from room temperature to 900 in a couple of seconds. The last one is the PECVD and LPCVD deposition. So basically you deposit, so it's highly used for silicon nitride, silicon dioxide deposition. That is widely used for fabrication or for passivation. So you can use them as a passivation for silicon nitride, also the other one, and also as a sacrificial layer. And we check, of course, the quality of deposition with a bunch of parameters like composition, contamination, mechanical properties, electrical, and so on. We measure, for example, the reflectivity, and these are the tools here. So I try to speed up. Hope I'm not too late. This is a very basic process flow here. So you start with the as-grown nice wafers from partners. Then you need to isolate your device and form the ohmic contacts with, as I mentioned, metal deposition and RTA, so rapid thermal annealing. You deposit your gate, passivate your device, and then also pattern the backside or etch eventually, depending on the application. So this is how it looks when the device is finished. So this is just a sketch here and the focused ion beam view of the device. These are the Ohmic contacts. You can see the gates. This is field plate to manage the electric field. The black layer is PECVD, nitride passivation. You can see that, again, it's everywhere. And these are layers with in situ nitride that you cannot see because it's too thin here. So I go through a couple of main steps in processing. So Ohmic contacts, which is obviously fundamental building blocks of GaN power devices. So what we need to reduce here is the contact resistance. I think Peter yesterday described quite extensively already. So this contact resistance is the sum of the metal resistance, the resistance of the barrier layer, and the resistance to the two deck here. So what you need to know is achieving good Ohmic contacts in this kind of materials looks simple, but it's everything but simple. It's inherently difficult, and this is due to the band gap. You have to go through a very wide band gap. So it's good for Schottky, but it's tough for Ohmics. And typically the Schottky barrier height on this material on N-type is about 1 eV. That's also what we get on HEMTs. And for P-types it's even worse due to, let's say, worse doping, and it's about 2 eV. So, and there was also something mentioned also previously is when you increase the aluminum content, it makes wider band gap and it's even more difficult. So how do we form the Ohmics? So you do a litho. Now you know what is a litho for people who are not used to it. So you do surface treatment. This is really key, or even etching. So that's really crucial to make right Ohmics. Then you deposit metal, which is typically based on titanium aluminum for GaN heterostructure, and then you anneal at a certain temperature, which is also a key here. So very quickly, this is the band diagram to describe the, I know you're tired, so this is kind of becoming more heavy, but this is not that complicated here. So to describe the mechanism of the current transport after annealing, so what you have here is the model assumes the presence of a modified surface. You can imagine after such a high temperature treatment, you obviously modify the surface here. And subsequently to this high temperature, so the electron can easily go through, but then you have still to go through this barrier layer here. So the second barrier is the one that you need to, where the electron needs to be injected to overcome and reach the two deck. So how do we measure the contact resistance? So I will go fast because this has been also described yesterday. So the total resistance, this is what we call a TLM, transfer length measurement extraction. It's actually very simple. So if you look at your total resistance, it's related to the metal resistance, the contact, so the barrier layer, and the semiconductor resistance. And usually the metal resistance is very negligible. It's like 0.1 or something or millimeters, so you just remove it. The semiconductor resistance is the sheet resistance by the length on the width, which gives you this equation here, and you can extract, you can plot, I mean, with different various spacing on a scale TLM, you can plot this line and extract the contact resistance as well as the sheet resistance based on this very simple equation. Is pretty accurate, especially if you use 4 probes to let's say, avoid or to prevent the resistance from the probes. And again, as I mentioned before, so surface treatment or etching is a key, and also temperature. So for, let's say, for doing good Ohmic contacts on any semiconductor, you always, if you plot as a function of annealing temperature, you always have a minimum. If you use the right metal stack and the right surface treatment, then you get the lowest resistivity as possible. So which looks like that. So of course, gold is a big issue for the reason I will mention. It's good electrically, so most common solutions for Ohmics are based on titanium, aluminum, separation layer like nickel, molybdenum, whatever, and gold, multi-layers. This provides you really state-of-the-art contact resistance without any doping, so it's about 0.2 or millimeter. And the gold helps a lot, more than what people think, I guess, since it enabled mainly to prevent surface oxidation and also improve the contact resistance by the formation of conductive phase. So it helps for the conductivity of the created phase inside the entire metal stack. However, this is not acceptable for power devices, and the reason is simple. It has to be low cost and fully compatible with silicon CMOS technology. So this is something we cannot overcome. So therefore, they want to avoid any cross-contamination. So gold is definitely not acceptable for manufacturing cost and so on. The good point is that very low contact resistance, so well below 1 ohm millimeter, which is very good value. It's a half ohm millimeter here. In this case, has been already demonstrated. It's available in literature. This, in this case, was like titanium, aluminum, tungsten ohmic contact. But I guess this has been developed by companies like onsemi. They have also these types of value, most probably in thousands of wafers. So this is, I guess, well controlled now, without gold. So device isolation, so this is the past, I would say. We used to do MESA, we did a lot of that. So basically, if you want to isolate, you just need to etch deep and cut the 2DEG, and that actually works. But that has many drawbacks because of this leakage that you easily create, especially at very high bias. So this is something you may not see at 200 volt, but if you go to a kilovolt, you will suffer from these things. So to my opinion, MESA is not a viable solution for isolated properly device, especially at high voltage. So what we use, what people use is implantation. So what I described previously, so implantation, it's completely planar surface. It's highly reproducible, stable. We've never get any issue with that, and the isolation is outstanding. So this is the solution which is used for isolation. Gate model, I again don't have time to go in details, but normally it has been mentioned yesterday. It's definitely designed for GaN power electronics. So the reason has been mentioned also. So you can get various architectures. The first one is the Schottky contact. So you just deposit your gate on top of your semiconductor. This is the simplest structure you can get, but for power, again, this is used for RF because you want the shorter gate to channel distance, but for power, this is not an option. As you get high leakage current, rather high leakage current, at least it's not acceptable with the criteria of 1 microamp per millimeter at high voltage. So this is not viable for power GaN devices. This obviously reduces the breakdown voltage, and it's definitely normally on devices here if you don't etch anything. So also a solution which is of interest for many groups is based on PGAN. This has been also described. So you basically have a PGAN layer under the gate that you etch, of course, outside the gate to form the 2DEG. Here, this gives you low leakage, so you deplete the channel here under the gate, but of course you remove it here outside. So you have low leakage, you have a single chip, normally off transistor. One you can criticize also, I mean, one of the weak point may be the threshold voltage. You can always argue how high the threshold voltage should be. Is it 1.5 enough? I cannot answer, but at least you don't get such high threshold voltage. Again, this can be improved by playing with the junction, with the design, so this is also something ongoing. Another solution is basically to etch through the 2DEG, deposit a dielectric, usually by ALD, for example, and you also get low leakage owing to this dielectric. Single chip normally off transistors, but here clearly, to my opinion, maybe I'm wrong, but I didn't see any qualified devices because of this device dielectric, semiconductor dielectric interface. This has not been solved so far. I know many people are still working on that, but today it's not solved. So that's not the. So it's a difficult solution, I would say. Okay, I'll go to the last part of my talk. This should be fine. So this is more related to the InRel project, where the consortium is here. So one of our tasks again is to develop a local substrate removal. It's really a lot of fun, and it's quite interesting. So we're happy to do that. So I'll give you, before starting on this approach, I just want to remind for some people or to show you how it breaks. And what is the breakdown mechanism in GaN on silicon? So this is true for any type of heterostructure, whatever you have, AlGaN, aluminum nitride, whatever. So if you have so the breakdown depends on the gate drain distance here. So if you take a short gate drain distance, like 2 micron, as used for RF, for example, you will break down at the gate vicinity in the 2 deck here. And that's what you have, a very sharp increase of the leakage current off state here. So if you increase the gate drain distance, you increase the breakdown. So this is not a great layer because you have this bump here that is obviously solved, but whatever, it doesn't matter for this example. And you keep increasing the gate drain distance, you keep increasing the breakdown for a certain value. So you can see here that with 10 micron, 15, 20, 30, you always have the same breakdown, hard breakdown here. So you have a strong saturation. Actually, the breakdown occurs at the buffer silicon interface. So this really shows that your weak point is actually the silicon substrate. And so that's quite clear from this point. So what people do for that, to overcome that, and to push the limits is basically to increase the thickness of this stack. So you will, again, deplete, but you will have a much higher resistivity, much higher thickness, so you will basically increase the breakdown. This has been shown quite a long time ago by Japanese, and it works perfectly. So they showed that you increase the buffer thickness, you increase the breakdown voltage, they reach very nice value. This is lateral breakdown above 2 kilovolt. But you can see that the thickness of the buffer is huge. We are talking about 7 micron. For growers, they know this starts to be very difficult, and this starts to create issues also in terms of, as explained nicely in the previous talk, in terms of defect density and strain. So there is a question mark here. Can you use more than 6 micron? And even if you use it, I'm not sure you can get the right reliability. So you can't keeping increasing the buffer thickness. So that's the message here. So maybe 6 is fine, maybe 7, I don't know. But there will be very quickly a limit of how thick you can go. And to my knowledge, is around this value today. So another way that we thought to overcome these issues, just to remove the substrate. This has been, I mean, the idea is not new, it starts to be old. But the question is how to make it reproducible, how to make it in large, let's say, large area and so on. So this should enable, if you remove the silicon under the device, it should enable drastic increase of the breakdown, and you don't need such a thick buffers. So that's the work we're trying to do within this InRel project. So first what we do is, of course, the front side of the wafers. So we fabricate devices, Ohmic contact, isolation, gate model that I described. We passivate, we make interconnects. This is a normally on, this could be a normally off. If you use PGAN, it doesn't matter here. So in this case, just for demo, we use the simplest technology as possible. So, and the silicon nitride is a dielectric, so it's definitely a normally on that you can see here, minus 5 volt pinch off. And you can see the nice off state, that's the gate leakage all the way to 1.2 kilovolt. And that's the drain leakage that starts to increase. You have a hard breakdown around 1.2 kilovolt, which is decent value for the thickness that has been used here. This is an image of the front side SEM of the device. So fully functional device. So what we thought first is to say, let's remove everything. Let's remove the silicon everywhere. So we tried on large area. In this case, it's 2 centimeter by 2 centimeter. And this is what you get. So I'm not saying it's impossible. Never can say that in technology, but it's everything but obvious. So in our case, we systematically get breakage of membrane. This is highly strained, so we never managed to get such large area with nice film. So you can imagine you have a couple of micron of it's just the heterostructure here. So so what we thought when we saw that is say, let's do it locally in a very small, let's say, millimeter square area, as the strain issue should be significantly reduced. So that's what we try to put in place, and that's the process flow here. So we start with a very thick substrate, and the reason is simple. Thick substrates are used to handle such highly strained heterostructure. So it's about 1 millimeter. It can be a little bit less, a little bit more. So we thin and polish down to 200 microns. So that's the first step. Of course, devices are fully completed. Okay, so we now put that on a carrier and engineer the backside. And then what we do is a photolithography using laser writing, deep etching using a Bosch process. The good thing is it's highly selective here. So when you etch the silicon, you have a very high selectivity with the aluminum nitride nucleation layer. So it's pretty easy to stop at the right place, I would say. That's what we call membranes. So they have the silicon here. They still resist on top. It's not cleaned up yet. And this is what we call the membrane, so a couple of microns here. So it's reversed, basically. So to have a better view, this is the backside view of the silicon removal. That's just the layout of the device. Why I put the layout here is just to show you that on the same layout, we have devices etched and devices non-etched. So if you want to have a very nice comparison, you can do two samples. This is too complex technology. So what we do is we compare on-wafer devices with and without backside removal. So then there is no variation of processing or whatsoever. So you can see a small device, 2 × 50, which is fully isolated from backside with a distance above 50 microns. This is also a key because at the bias you will see it flows everywhere, even through the pads. And this is a larger device also to show you that in terms of pure etching, you can etch very large membranes. So this is a 10 millimeter width devices here. And here's the real view of that's a real device, so with some etch device and some non-etch where you can see the silicon here. Of course, when you etch the membranes, you need to replace the silicon. You cannot just leave the membranes. It's not viable. So you need to put something and reconstruct somehow the substrate. So there are not so many choices. You need something low cost. You need something that is wider bandgap than gallium nitride. Otherwise, it doesn't make sense. So what we call the ultra-wide bandgap. So aluminum nitride is definitely a good candidate because one of the main reasons is the cost. This can be done by PECVD, so plasma vapor deposition, this on very large area. So I'm not expert of low cost. This has to be checked, but to my opinion, this could be very affordable, I would say. And the important point is the temperature deposition. It has to be low because you have already, it's a post-process. So all your contacts are there. So it has to be, let's say, lower than 350. So we use about 300 degrees C here. And already with such a low temperature, the breakdown field of this film is way, way beyond gallium nitride. It's above 4 megawatt per centimeter. We don't even have the right value because that's the limit of our setup, even though we upgraded recently. We measure different films. And you see, we have 3 kilovolts here, so we don't really know. It's probably better, but it's at least 4 megawatt per centimeter, so it's very high breakdown field. Of course, the thermal conductivity is not that great, but that's another story. So we, on the same wafer, can compare this type of device, so fully completed with the silicon, and the one with membranes and aluminum nitride thick deposition. This is a small device here. You can see a shift, so you have basically very similar devices. You can see a shift of threshold voltage. We didn't investigate yet, but we believe that the fact it remains a couple of hours at above 300 degrees C after full process. So you may see a shift of VTH after such a long temperature stress somehow. But anyway, if you look at off-state characteristics, this is really day and night. So this is what you get. I showed you before. This is what you get on silicon, the black one, and you have breakdown around a little bit above 1 kilovolt. That's the same device. And with this ultra-wide bandgap, that's what you can get. And the amazing point is the leakage level. So that's really a key because the criteria, as unlike RF devices, is 1 micron per millimeter. So this is really and it's easy to understand. If you have milliamps at 1,000 volts, this would be a crazy power at such high bias. So, 3 kilovolt below 1 micron per millimeter. And for people who are not in the field, this is really quite unique because if you compare the result with this criteria, there's nothing comparable so far. So, and the only way is to remove the silicon and change the material. That's beyond the intrinsic properties of gallium nitride. So I don't think there is a way to get such large buffer thickness to reach this value. I think it's not viable also from buffer thickness point of view. So this is a nice result that, of course, we're not, the wafer I didn't mention, this is coming from EpiGaN, and this is done within this project here. One of the next steps, which will be very challenging, is to perform that on larger devices, so let's say 1 centimeter and above. So we are working on large membrane. I didn't put the picture, we have some work that we will discuss tomorrow, but we are working already on let's say, membrane area compatible with 20 amps devices, so large devices, basically. So I just want to conclude, this is my personal view of what is going on in the future. People like to talk about the future. So only 1 or 2 slides, sorry for the time. So there will be everything but the end of silicon. So, you know, some people talk about no silicon, gallium nitride, 100%. Of course, this is everything but that. I call that end of silicon domination. This was 99% silicon. They should, you know, the rate should change, and with the introduction on the market of new material, and the best example is that large, big companies are using gallium nitride, developing gallium nitride, hopefully make it everywhere somehow. And GaN on silicon is one example, but there should be many others in different, and also in RF. So in the end, you want to combine this CMOS outstanding technology with for achieving highly functional systems. So that's one of the trends. And yeah, I'll leave you with that. So as there are many PhDs here, so it's time for opportunity for newcomers, young researchers. It's not an established, let's say, arena. So there are places for new people, and because of this transition towards new materials. This is already true, but this will be all the more needed. So multidisciplinary, so growers, material, device people working together to overcome this future challenge. And as mentioned by Peter yesterday, so cost is definitely, unlike niche application, for widespread application, cost will remain the main figure of merit. So the physics is nice, new materials are nice also, but it has to go along the cost if you want to see it happening somewhere. So thanks for your attention.
Thank you, Farid, for your presentation. It's time for some questions, if any. Okay, I have just a question for you. So concerning this gate architecture for normally off devices, what do you think, how can you comment about the P-gate and the D-presses with MIS structure? So when you see, which time frame you see for the P-GaN, is that that can last forever, or is just a matter to wait for a well-established D-presses MIS structure that will kill the P-gate GaN structures? Or what's your opinion on that?
To be honest, I'm a big defender of P-GaN, so again, I don't have the answer. But to me, I'm not sure you can solve the insulator semiconductor problem interface. Mm-hmm. The surface is charged. So my feeling is whatever you do, you will have to suffer from something. Okay. So it's gonna be very difficult for MIS. P-GaN with some nice boundary, with the threshold you get, you can use it. Okay. If you don't go to very high forward bias, for example, and if you limit the safe operating area.
Okay, good. Any other question? So if not, let's thanks again Farid for the nice talk.